So, Chapter 3, logarithmic and exponential functions. They are related. This is an introduction, so we're going to give you bits and pieces of what the rest of the chapter looks like. Starting with, let's do something new. Let's do a graph, shall we? So an exponential function, you know, that thing is an exponent, right? So if we graph it, it's an exponential function. Well, even if we don't graph it, it's an exponential function. So exponential growth or decay, you guys have done it. I know I taught you it in Math 11, and you've probably seen it in other courses too. So anything that looks like that, by definition, is an exponential function, as long as we get some of the technical stuff out of the way so that professors are happy. Okay, b has to be greater than 0. So for example, what does that thing look like? That's in this form, but we've kind of simplified it. Where's the a here? B is the variable to which x is the exponent of. Okay, so it's the base. So that's b. What's a here? Yeah, okay. So we've simplified it. A is 1. So don't go, well, A is 2, what's B? Okay. So quickly, as a table, what's going on? I got x minus 3, so let's go to minus 3, minus 2, minus 1, 0, 1, 2, 3. And that's it. That's my whole graph. If x is minus 3, then I have 2 to the minus 3, but remember in grade 10 we don't really want a negative exponent, do we? How do I make that thing positive? By flipping these, okay? Or take the reciprocal. So 1 goes up there, this goes down here, and everything stays the same. The only difference is now it's positive. What's 2 times 2 times 2? 8. So this is 1/8. If you don't believe me, put that in your calculator. You get 0.125. Okay? So if x is negative 3, let's make it a decimal. Y is, looks like about 1/8. Okay? If x is negative 2, this is 1 over 2 squared, which is 1 over 4, otherwise known as a quarter. Okay? If x is negative 1, then this is just 1/2, right? If x is 0, what's anything to the 0 power? One, right? Recall? A couple of you are looking kind of confused. Well, don't believe me. Maybe I made a mistake. Okay, I didn't make a mistake. It's 1, right? So 0, I got 1. 1. What's 2 to the 1 power? 2. What's 2 squared? 4. What's 2 cubed? 8. And wouldn't you know it, look at that, my scale works perfectly. Okay. So, does that look like a straight line? Absolutely not. Exponential growth. Think multiplying cells, bacteria, money in a bank account. Okay? So there b was 2. What happens if b is 1/2? A little harder, but again, negative 3. What is 1/2 to the negative 3 power? And you might be thinking, well, okay, I'll take 1 over it and make it positive. What's 1 over an eighth? How many eighths go into 1? 8. Or if you remember the trick in grade 10, to make that positive, all I have to do is flip these guys around. Okay, and then that's 2 to the 3 over 1 to the 3. It's still 8. Negative 3 is 8. So negative 2 is what? 2 squared over 1 squared, that's 4. Negative 1, whoop, 1/2 to the negative 1, flip them and make it positive. What's that? That's 2. Anything to the 0 power is still 1. See a little pattern here between this graph and this graph? Positive 1. 1/2 to the 1 power is a half, right? 1/2 squared, excuse me, is 1 squared over 2 squared, which is 1 over 4, which is also known as a quarter. And that one's going to be, yeah, same thing we got over here, isn't it? So, very, very similar. I wouldn't call this growth. I would call it what? Dying? Yeah, kind of. It starts with a D. You've done some radioactivity questions in science, haven't you? Science 10? Where they talk about half-lives of plutonium or uranium, and yeah. Well done, Destiny. Excellent. Okay? That's decay. You saw graphs like this. So, this will always happen. If the exponent here, well, if b, let's just read it as it says. If b is greater than 1, you're going to have growth. If it's less than 1, you're going to have decay. Because anything less than 1 multiplied by itself gets to be a smaller and a smaller number, right? Everything bigger than 1, like even 1.1, multiply it, and it gets bigger and bigger and bigger. Okay? So, that's some graphing stuff. Compound interest. Albert Einstein was quoted as saying, this is one of the wonders of the world. And in Math 12 Foundations, we actually spend like 2 months on this stuff. Pretty kind of cool. Got a little story about the Red Indians of Manhattan. Has anyone heard it? Well, in a nutshell, I show this with the actual numbers, but let me just say it. When Europeans came over to, you know where Manhattan is, New York, apparently they gave the indigenous people there about 20 bucks. Said, we'll take this island off you. And they said, okay. Now they had no use of the money, $20, but they gave them the equivalent of $20 of beads and trinkets and maybe a bottle of firewater or something. Okay, does it sound like they got ripped off? Right now the real estate on Manhattan is just, the real estate alone is worth about $2 trillion. But this was in 1626. Now, if they had taken that $20 and put it in a bank account for close to 400 years, on average, that's what they would have gotten. Okay? Right now, we're getting, you're lucky if you get 1.5% in a bank account. But back in the 80s, you got 20% on your money just for sitting it in the bank. Over the last 400 years, that's what it's averaged. Do you know what they'd have? $4 trillion. $20 at 8% a year for 400 years, give you like 4 trillion. Don't quote me, it's approximate. So, had they done that, they would have had more than the value of Manhattan. But they didn't. So I guess you could say they got ripped off. Compound interest. One of the wonders of the world. So we have 1, 2, 3, 4, 5 variables in this thing. Okay? A is the amount or the future amount. P is what we start with. In money terms, it's called the principal, spelt the same way as Mr. McGoldrick. Not principal, L-E, like the main point. But a lot of times we'll call that the present value, because, prevent. If this is the future amount, then what we have now is called the present amount. Okay? Either or. It's P in both cases. I is the interest you'll get on that money. If you're investing, that's what you get. If you don't have money, you need money, you're called a borrower, and that's what you pay. It's interest in both cases, right? This is annualized. That's an annual rate. When they say 8%, they mean per year. It's understood, right? So annualized rate, yearly. The problem is, things aren't usually yearly. Like mortgages, by law, they're compounded semi-annually, every 6 months. Don't ask me why, they just are. Everyone has to follow the same rules. Okay, so N makes this different depending if it's a year. If it's a year, then N would just be 1 here, and we don't have to worry about N. But we could have monthly, weekly, bi-weekly, semi-monthly, daily. Okay, there's lots of different choices here. So what N is the number of compounding periods. And then T, of course, is the time. Usually we don't invest things for 400 years because we're not around to spend the money when it comes back out, right? But someone's great-great-grandkids could. All right, so annually, N would be 1. That would be the easiest case. Monthly, we know how many months are in a year? Yeah. So if it's compounded monthly, it's compounded 12 times a year. So 12% per year, if that was 1% per month, you'd end up with a lot more money. Not a lot, but significantly more. Okay, because it's compounded more often. You get interest on the interest. Do you understand this principle? Copy your nodding? Okay. Yeah, and then the tough questions, like how many weeks are in a year? See, but that's why there's not, a lot of people, you ask them how many weeks in a month? They say 4. It's not correct, right? Because 4 times 12 is 48, not 52. That's just a rough approximation, right? Bi-weekly. How many wheels does a bicycle have? So this is every 2 weeks. There's 52 weeks in a year. So if this is compounded bi-weekly, that's 26 times, which is different than semi-monthly. Semi is a half. I'm thinking of a truck right now. I don't know where that comes from, right? But semicircle, half a circle. Semi-monthly, half a month. So every half a month, there's 12 months. So this would be 24 times a year, right? So they're different amounts. Daily, of course, we approximate it to 365 days a year, but we know that's incorrect. We know our years are out by a quarter of a day every year, right? Okay, so some examples. There's a formula. Steve invests $12,000 at 11.5% per, what's A stand for? Well, no, sorry, not in the formula. That says 11.5% per year, right? But this is understood. You don't even need that. If it says 11.5%, that means per year. But this is compounded monthly. It's actually, let's write this right here, right? So here's our formula. Okay, they got lots of variables. I got to know them all except one. Let's start with the easiest example. How much do I have at some point in the future? If I put away 12 grand, and good luck getting 11.5% these days, but anyway, that's the question. That's the principal or the present value today. 1 plus 11.5%. I want that as a decimal. And we know how to do that, right? Just move it 2 spots to the left. But this is compounded, not yearly, monthly. So n is monthly. Ooh, n's 12. Okay? So 12 goes down here, and then n is still 12. There's also an n up there. T is the time, and it's going to be years, okay? Usually, like 99% of the time. Okay? So before I actually plug that in the formula, let's see, does it kind of make sense? Like if I got 11.5% per year, I would just go 12,000 times 0.115. That would give me the interest for a year. This is compounded 12 times a year, right? So I get whatever 11.5 is divided by 12, just a little bit less than 1%, but it's compounded monthly for 2 years, 24 times. Does that make sense? So monthly, 24 times. So this is the compounding period, okay? And I want a monthly rate. So it should kind of look like it makes sense. $12,000. Bracket 1 plus. Now what the 1 does is give you not only the interest, but give you the $12,000 back. Okay? So you don't have to calculate the interest, then add it to the principal. This does both at the same time. To the power of 24. Does it look reasonable? Like it shouldn't be a million after 2 years. That would be crazy, right? And it's got to be more than 12,000 bucks. The same reasonable? So 15,000. This is money. We don't want 0.6697. We round it to the penny. Actually, these days we round it to the nickel now, don't we? 15,086 bucks and 67 cents. Okay? Now vice versa. If you borrowed 12,000 at 11.5%, compounded monthly for 2 years, that's how much you'd owe. Right? It's the same thing. If you have money, you invest it. You borrow, you lend it to people who don't have money, and it makes the world go around, right? Okay? Let's do something a little harder. Jesse bought a house for $250,000. That's how much he spent on it today. 6 years later, she, that's a female, sold it for $600,000. Good luck. So in the future, that's the amount we got. Now everyone wants to go out and buy a house, right? It's just that easy. No, it's not. What was the annual interest rate? And we're going to assume it's compounded annually. So n is 1. So 1 plus I over 1, n is 1 times t. Do I know what t is? Yeah, so let's actually put that in there, okay? So I'm solving this thing for I. What do I want to do first? First of all, do I need all those zeros there? Let's cross out 4 of them. That's 60. That's 25. Let's divide by 25 with 60 over 25. .4, and let's rewrite it. 1 plus I to the 6th power, okay? So I want to know I want to get I by itself. How do I get rid of that exponent of 6? We did this in grade 11 math, right? You guys remember? Remember Pythagoras? How do I get rid of this 2 here when I've done all this, and that's, I don't know, 48.6? Yeah. Okay, because that kind of like cancels this out. Well, how do I get rid of this 6? Take the 6th root. Whatever you do to one side, do to the other side. So the 6th root of the 6th power is nullified. There's a weird word. So I just have 1 plus I is 6 the root of 2.4 is 1.157. How do I solve that for I? Minus 1, minus 1. I is 0.157. What's that in percent? 15.7%. It's a pretty darn good rate of return, I would say. Okay? By the same token, if you're a little kid and you put in 25 bucks in your bank account, come back 6 years later, if you got 15.7% compounded annually, you'd have 60 bucks. All right? So there's some money problems, money questions. Again, like I said, this is an introduction, right? We're going to do a whole day of this stuff. We're just kind of just showing you what we can do with the logs and exponentials. This is extremely similar to the formula we just looked at. It's just for different problems. It's not for money. It's for growth when it's not money. Okay? So we don't have a percent here. It's not 1 plus I. It's just substituted for x. And I've seen it in other forms as well. Okay? So A again is the future amount. P, there's no principal here, it's not money. So it's the present value or present amount if you want. X is growth. The growth, or maybe it's decay factor. Okay, and if we're talking about half-life, then obviously that's decay. T is the time, and N here we'll call something different. Okay, it's the half-life, or for these examples, the doubling, and maybe it's going to be tripling. Okay, but that's not the compounding period, it's the half-life or doubling time. Some questions might say triple, same thing. Quadruple, same thing. 10th, okay? But pretty much the same thing as money. I don't know if this is accurate, but according to this, Ebola doubles every 30 minutes. Is it? Okay, someone did their research. Good. I assume it's Mr. F. So there's the key word. This is the doubling time, right? 30 minutes. N is 30. X is, what's the number for the word double? 2. Okay? It's kind of like the first thing we did here when we graphed this. There's doubling. We just don't know how long it doubles for. There's currently 2,000 Ebola, blah, 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 blah. How many are present in 7 hours? I want to know what A is. So A is P X to the T over N. I have 2,000. They double. 7 hours. 30 minutes. These don't jive, do they? It's a technical word. So I don't care if you put them both in minutes or you put them both in hours. What would be easiest here? 30 minutes is half an hour, right? So 7 over 0.5. So they double 14 times, right? Could you do this the long way to slow boat to China method? Sure you could. Put in your calculator, take 2,000, double it 14 times. You'll get the same answer. But let's do it the big kid way. 2 power of 14. 3.2 million. A lot of Ebolas. Is Ebola plural for Ebola? I think it is. Ebolas? Okay, whatever. So, like I said, if you went 2,000 14 times, double, 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 okay, you'll get the same thing. Okay, 2 more. Strontium-90 has a half-life, X is a half, of 250 days. That's the half-life time. There's 50 grams presently. How much is after 2,000 days? So the common sense way, maybe, if you didn't even know the formula, is how many times does that go in there? How many times does it have, right? But we want to use a formula. We start with 50. That's in grams. It halves. Okay, I've got 2,000 days, but it halves every 250 days. Okay, notice all my brackets? Look reasonable? That says 0.195 grams. Okay, we better have less, right? Because it's halving. Okay. Last one. So I think, if I recall, most of your assignment are questions like this. Mr. Epp currently has, this is way off, because I've looked this up before. The average person starts with about 150,000 hairs. Okay? If you got red hair, it's more like 100,000. If you're Asian, it's maybe 150, 160,000. And if you're blonde, it's somewhere in the middle. Depends how coarse your hair is, right? Black hair is thinner than blonde hair, which is a lot thinner than red hair. So this is way out to lunch. But anyway, he started with 3 million. His hair decreases by 3% per year. Okay? How long will it take before he gets to 1 million? And we got a picture here to graph it. So 3, 1. You don't want to put 3 million in your graphing calculator. Okay? Let's just call that millions and put 3, 2, 1. It starts at 3 million. It's going to decay down to 1 million. I want to know how long that takes. As a formula, 1, do I need to put 6 zeros here? No. It's the same as I started with 3 hairs. When does it take till I get to 1 hair? Okay? Because as we saw before, when I divide those, okay, it doesn't matter how many zeros I get. It's just 2.4. Now, the tricky part is, what do I do with this? It's not doubling, it's not halving, it's going down by 3%. What's 1 minus 3%? 97%, right? So each year I have 97% of the hairs that I had the year before. That's a number less than 1. That is decay. Okay? Make sense? Okay, so x is 97% as a decimal. That's 0.97. I think we saw that in Math 11. I think we did. So, t what's n here? I'm going to assume it's yearly, okay? Doesn't say anything else, so n is 1. So that makes it kind of nicer. Now, we saw this stuff in Math 11. You know what I told you then? You don't know logarithms, so you have to do that by trial and error. So when is 0.97 to the power of t equal to a third? And in Math 11, you remember doing this? Yeah, 0.97, I don't know, let's go 10. Is that a third yet? 0.3333? No. 0.97, I don't know, let's try 20. 20 years. Getting closer, okay? 40 years. Is he even going to live that long? Oh, it's between 30 and 40, 20 and, oh, I just jumped right from 20 to 40. Is he going to live 30 years? I think so. But it's more than 40 years, right? So it's been in between 40 and 50 years. I could narrow this down. Is this how we want to do it? No. We're going to solve this with a logarithm. But let's actually, everyone's got their graphing calculator? When is that going to be equal to, now let's check our window. I don't want any negatives. That doesn't make any sense. So get -1. X, it needs to go to what? At least 40, right? Let's make it 50. Don't need any negatives here. And Y, I don't want to put in 3 million. I just want to put in 3. That should be up at, oh, I know what I didn't do. I don't want to plot that. I want to plot this. All right, because I start at 3 million. That's what I want to plot. So let me fix that. Insert 3 times 0.97. There, now I'll start at 3 million. So when does that get to 1 million? I could go trace and kind of go down till y is about 1-ish, but that's still approximate, isn't it? That's pretty close. 35.9 years. How do I make it exact? Let's plot 1. And then I'll find the intersection of those two lines. That'll be exact. Second function, calculate intersection between that line and this line. In 36.07 years, he'll be down to 1 million hairs. So if you got a tool, use it, right? So that's what this thing looks like. You can put in that, and that's right there. So for Windows, I went -1 to 50, and Y -1 to 3, assuming that's in millions, right? And this is what I plotted. Okay? Okay, because that's a lot quicker than doing this. 0.97 to the power of 36 is pretty close to 1/3, 0.333. Okay? So, I know I gave you lots of stuff, okay? Don't freak out. This is the whole chapter. I'm just giving you all kind of at once. And then each day we're going to work on it and build in it. But of course you want to finish your assignment, right?